Hey, it's Executive Editor Stephen Lacey. Many of you were loyal listeners to a show I created and co-hosted for 8 years called The Energy Gang. Well, we're back. Jigar Shah, Catherine Hamilton, and I are excited to announce our latest project, a weekly news roundtable called Open Circuit. Every week we'll break down how major projects come together, how deals and policies get structured, and what it takes to build critical infrastructure at scale, all through the lens of current events. You can subscribe to Open Circuit wherever you listen to podcasts or follow it at latitudemedia.com.
Latitude Media, podcast at the frontier of climate technology.
I'm Shail Khan, and this is Catalyst.
So what I often tell people is that electrochemistry is powerful enough to break anything.
Coming up, bear with us. It's a love letter to electrochemistry.
Catalyst is brought to you by Antenna Group, the communications and marketing partner for mission-driven organizations developing and adopting climate solutions. Their team of experts help businesses like yours identify, refine, and amplify your authentic climate story. With over 3 decades of experience as a growth partner to the most consequential brands in the industry, their team is ready to make an impact on day one. Get started today at antennagroup.com.
The electric grid is changing. Utilities need smarter solutions to balance supply and demand, especially as they face growing renewables and electrification. With Energy Hub, utilities can manage all of their customers' connected devices, like batteries, EVs, and smart thermostats, in one platform to grow their virtual power plants and seamlessly shape electricity demand. Unlock the power of flexibility at scale and deliver more value through cross-DER dispatch with Energy Hub, the leading edge DERMS provider. Visit energyhub.com to learn more.
I'm Shail Khan. I lead the Frontier Fund at Energy Impact Partners. Welcome. So I've been wanting to do this one for a while. Here's one thing that has bothered me. In the startup world, which I inhabit, there are entire firms, like investment firms, dedicated to investing in the biotech, or sometimes they call it tech bio revolution. Just taking one random example, Andreessen Horowitz, which many folks know, they have a core venture fund, they have a growth fund, and they have a bio fund, which is all great. There's all sorts of interesting things going on in bio world, but I've always wondered why we don't see quite the same love for my favorite discipline, which is electrochemistry. In the greatest hits album of electrochemistry, you'd have a lot of tracks focused on batteries, for sure, and for good reason. But there are deeper cuts, too, and some new music with pretty extraordinary potential. Anyway, think tracks on cement and steel and fuels and mining and all sorts of other industrial categories, and heavy emitting categories, I should add. Anyway, in my opinion, electrochemistry needs more love and more understanding. So I brought on the perfect guest to talk through it with me. Yetming Chang is a professor at MIT, but he also is well known in the kind of climate tech startup ecosystem for having co-founded, I think, an unparalleled number of electrochemistry-focused startups in and outside the clean energy space. Among them are 2 EIP portfolio companies, I should add, Form Energy and Sublime Systems, but also 24M, Desktop Metal, A123 Systems, and even more than that. So Yet is prolific, both as an academic and as a generator of ideas in how to apply electrochemistry in the real world to decarbonize things. So with no further ado, here's Yet. Yeah, welcome.
Thanks, Shail. Happy to be here.
Excited to use you as my foil to write a verbal love letter to electrochemistry here. And I think there is no better penman than you to do that. I'm going to ask you maybe to start to just define electrochemistry for anybody who is not already familiar, and maybe tell me why it's interesting at the highest level.
Great. And as you know, I love electrochemistry, right? And so this is the perfect opportunity for me to talk about it. When I bring folks into my lab, I tell them I do electrochemistry, and I show them a lab apparatus, let's say a glove box, in which inside there are chemicals. There may be beakers, there may be solid compounds. And I show them below this glove box is all this electrical equipment, and there are wires leading into this glove box. And I say, well, I do electrochemistry. Here's the chemistry, and here's the electricity. Together, it's electrochemistry. To answer your question, a little more specifically, how do we think about electrochemistry and what makes it interesting? The key point to me has always been the fact that electrochemistry allows you to make chemical reactions occur that otherwise may not occur. Right? In particular, chemical reactions that may be very much energetically uphill. Now, if it's spontaneous, it's energetically downhill. It's going to happen on its own. But what about those that you want to make happen that are very much uphill? And so, my example for that would be something like a lithium-ion battery. Lithium-ion battery, the single cell voltage is about 3.5 to 4 volts. And if we just close the external circuit on a charged battery, it discharges. That's energetically downhill. Okay? But then, when we want to charge it again, we have to apply that 4 volts or so. May I geek out for just a second on this?
I expect nothing less.
Okay.
Go ahead.
So what's moving when you apply that charge voltage is a lithium-ion. So this is a lithium plus 1 ion, and it's moving across 4 volts. And so the energy you're imparting to that lithium-ion is 4 electron volts. That's a unit of energy, 4 electron volts. And it turns out that 4 electron volts is an absolutely enormous amount of energy. If we were to compare it to, for example, the heat of vaporization of water, it's about 10 times that. Okay? If we were to compare it to just temperature terms, thermal energy is equivalent to a temperature of 46,500 degrees Kelvin. It's an absolutely enormous amount of energy. Yet, we can sit there at room temperature, turn a knob, and make this reaction go backwards and charge that battery. Now, that's really cool. Right? Can I give you another example? So the power of electrochemistry, we think, how much is this energy? Again, how do we think about this amount of energy? And let me compare it to mechanical energy. So, mechanical energy, you take a solid, let's say, and you load it and you stress it until it breaks and has a strength. And, some materials have, very high strengths. And if we compare that amount of mechanical energy that you can elastically store in a solid, it is so tiny compared to electrochemical energy. So what I often tell people is that electrochemistry is powerful enough to break anything. Right? And one of the really interesting examples of this is actually in a battery again. If you take a freshly assembled lithium-ion battery, hasn't been charged at all, and we did this experiment. It was part of a thesis and papers, and you put on it a acoustic emission sensor. That's a fancy word for microphone. So you take this battery, you put on a microphone, and you start to cycle it. All this noise comes out. You hear snap, crackle, pop. And that's the solid compounds breaking due to this power of electrochemistry. Okay? About a decade ago, we recognized that electrochemistry had the ability to literally break anything, which means it could also deform anything. Therefore, we used electrochemistry to produce mechanical actuators. And one of the applications of those mechanical actuators was in a DARPA project where we were trying to make helicopter rotors twist in flight for aeroelastic purposes.
Yeah, so I think you've well described my impression of electrochemistry, which is that it's kind of magic. But my sense is that it was kind of a backwater field to some extent pre-batteries, and then batteries are the thing that really have driven. You've mentioned batteries a few times as an example because it is kind of the quintessential use of electrochemistry. But am I right to understand that there just wasn't that much going on in the world of electrochemistry prior to batteries, and that's what really has unlocked the field? Or was there more before that I'm unaware of?
Yeah, I wouldn't say it was a backwater. There's always been ongoing interest in electrochemistry. If you look at the scientific conferences that go on annually, there's always been, for example, a Gordon Research Conference. That's one of the premier no holds barred kind of open conferences. There's always been one on electrochemistry. The interest, I would agree that the interest in electrochemistry, and especially in how to use electrochemistry, has really exploded with the onset of the lithium-ion battery and all the things that followed that used electrochemistry that you're alluding to.
Catalyst is brought to you by Antenna Group, a powerhouse of strategists, storytellers, and industry veterans dedicated to elevating climate leaders. Antenna works tirelessly with enterprises, growth startups, investors, and ecosystem influencers to drive impact across energy, climate, and mobility. With over 3 decades of experience as a growth partner to the most consequential brands in the industry, they understand the trends and moments that matter and how to capitalize on them. Visit antennagroup.com to learn more.
Catalyst is brought to you by Energy Hub. Energy Hub helps utilities build next-generation virtual power plants that unlock reliable flexibility at every level of the grid. The Energy Hub platform takes the guesswork out of balancing energy supply and demand. It uses AI-driven optimizations to precisely shape load profiles and dispatch multiple types of customer devices for maximum grid impact. As the industry leader, Energy Hub helps more than 70 utilities manage 1.5 million devices, more than any other edge terms on the market. Click the link in the show notes to learn more, or go to energyhub.com.
I have, I guess, one higher level question that I've always been curious about. So you want to do some kind of chemical transformation. You can use electrochemistry, so you can apply a voltage and induce that transformation. In many cases, there are alternative pathways to do it. And so one that you see, just taking a specific example, say you want to produce sustainable aviation fuel, for example, right? There are electrical pathways that use electrochemistry to produce eSAF. There are also biological pathways. And that's true of a bunch of different categories where you have the, possibility of the competition between a biological pathway and an electrochemical pathway. Do you have a heuristic for what are the types of transformations for which electrochemistry is best suited, and which are the things that, what is it good at? What is it bad at?
Yes, great question. And I do believe, as much as I love electrochemistry, that it's important to be absolutely clear about where its limitations are. Okay. If you don't follow that kind of pathway of thinking about these problems, you end up with a hammer looking for a nail, and that's not really what you want to do, right? So one of the reasons the application of electrochemistry have become much more prevalent and interesting is because of this mega trend towards low-cost electricity. The lower the cost of electricity, the more attractive it is as an energy source. And that's what has driven many of these innovations. The mantra, let's electrify everything, right? That's certainly you've heard that, I've heard that. The limitation of electrochemistry is that it's a chemical reaction that takes place at an interface. Right? In a way, you could say that it's a two-dimensional process. You always need an electrode, and you need electrons being transferred at an electrode. And that makes it a two-dimensional process as opposed to a thermal process, which is a three-dimensional process. And that, I think, is the inherent limitation. We can take electrochemical processes at an electrode. We can increase the surface area, for example. Maybe we can get things to go up by a factor of 10, something like that. But it still has that fundamental limitation. So what you'll see in a lot of the innovations that use electrochemistry is that they don't use electrochemistry everywhere or in every step. You use it where it does the most good. And for example, decarbonizing cement with electrochemistry, that would be an example of that we can talk about.
Yeah, maybe walk through, because I think the two-dimensional, three-dimensional thing is a little bit intuitive, but it'd be useful to better understand it. Yeah, exactly. Take cement as an example. What are the parts of that process for which electrochemistry does make sense, and what are the parts for which it does not?
Yeah, so I'm referring to what we do as Sublime Systems, as you know. And the key thought process there was that given low-cost electricity, and how would you use that low-cost electricity to decarbonize cement production? And what we didn't think would work was simply using it for heating purposes. You can, of course, take electricity, turn it into heat, and power a thermal process that way. The pathway we took is one that has become interesting in a few other sectors since then, which is to use that low-cost electricity to create chemical reagents that will then do the chemical work for us. Okay? And that's a device called an electrolyzer. Most people know an electrolyzer from middle school, high school experiments where you split water, and what we would call a neutral water electrolyzer, starting with pH 7 water, and applying a voltage in the cell, something above about 1.25 volts, will split that water and gives you hydrogen and oxygen. But chemically, if you think at the same time about what happens if you're emitting hydrogen, you're starting with H2O and you're taking off hydrogen, you're going to be left behind, what you'll be leaving behind is OH, hydroxyl ions. The other end, if you're emitting oxygen, well, you should be leaving behind hydrogen. And so the end where you're emitting oxygen becomes acidic. The other end becomes, the other electrode becomes basic. And so you've created acid and base at the same time. So this idea of using low-cost electricity in an electrolyzer to produce acid and base allows you to produce acid and base for chemical reactions that then follow. And those chemical reactions can be done on a volume basis. And in fact, you can decouple in terms of time when you carry out the chemical reaction. So that those chemical reagents, the acid and bases, actually become a form of chemical storage of the energy that you got from low-cost electricity. So that general idea has now propagated to several different areas of mining. And for example, if you were to look at the ARPA-E miner program and the projects under there, you would find several that use electrolyzers to produce acid and bases for mining purposes.
And so the key insight there is that step, the production of acid and base, is well suited to this. If you have low-cost electricity, you can do it on a two-dimensional interface, whereas the chemical reactions that need to occur after that, you benefit substantially from an economic basis. You benefit substantially from it being a volume thing that you could basically do in a tank, essentially, as opposed to on a plate.
You want a big tank. That's right. You want a big tank in which everything's reacting all at once rather than making it all happen at an interface.
Okay, so cement is a good example. Mining is another good example. What are some other areas where there's like an interesting intersection of electrochemistry, or I guess emergent capabilities of electrochemistry up against what otherwise would have been or has been like a thermal process or a biological process?
Well, so SAFs, sustainable aviation fuels, would be an example. And in particular, CO2 to fuels. That is a case where CO2, decomposing molecules is highly energetic, and that's where electrochemistry has that advantage that I referred to earlier. Dial in with voltage, a high electrical potential that can drive a reaction that otherwise thermally is very hard to make happen, or essentially impossible to make happen. Right? So transformations from gas phase to fuels, from liquid phase to solids even. Earlier we talked about some of the limitations. I would say that one of the other limitations of electrochemistry, something it's not very good at, is solid-solid transformations. Okay, why would that be? It's that one of the things you have to have in order to make electrochemical reactions take place is that you have to have some electrical conductivity. You have to be able to move electrons around. And solid particles, especially insulating solid particles, just don't have that conductivity. And so those transformations, when you force them to take place at an electrode, tend to be even slower, more sluggish. Right? Which isn't to say you can't make that happen. In fact, we have some projects in which specifically we think we have a way around that. But that's a general limitation, solid to solid transformations.
You mentioned one of the core principles of what makes electrochemistry exciting, which we should dig into a little bit more, which is like the availability of low-cost electricity. That I think what we've learned over time is that, one, to some extent, there's a fight for low-cost electricity, certainly now, today, right? If you have low-cost available, significant capacity electricity, you're fighting up against a data center probably, or something else. But then the second component of it is that to the extent that there is really low cost electricity, absent places that, and particularly if you're looking for decarbonized electricity, absent places that have hydropower, you're talking about low cost electricity that is sometimes available. So like your curtailed wind or your overgenerated solar and things like that. One of the areas in which I think electrochemistry can shine, but does not always shine, is in the ability to operate intermittently. Can you just talk through what are the dynamics that determine whether a given electrochemical system can operate at partial capacity factor, can ramp up and down to take advantage of cheap electricity if it's only available some of the time?
That's right. And of course, that's one of the roles of large-scale grid storage. And what we do at Form Energy, right, is the ability to store and buffer those variations. But this example with electrolyzers that I mentioned earlier, we initially started off that project thinking that we would do everything inside this one device called an electrolyzer. Split water, make acid and base, or split salt, actually, make acid and base, carry out the reaction. And then we realized that actually storing the acid and base made a whole lot more sense because it allowed us to accommodate the intermittencies and have a form of storage. So I think that just in general is the role. We should think about how to, of course, the first part of the problem is what are the implications for CapEx if your capacity factor is not close to 100%. Can't really get around that. It is what it is. But the ability to run processes continuously downstream of that is where having some form of storage, I think, is important. That's what you have to think about doing from day one.
Yeah, I think that's one thing that people maybe don't fully appreciate. So you could sort of solve for the intermittency of the input electricity in two different ways. One is you could literally add batteries. You can add a separate thing that is a battery, and that can be power to power. It could be a form battery. It could be power to heat with a thermal battery, whatever it is. But you can add a battery, or you can design your system such that it sort of effectively has a battery within it, has a form of storage, energy storage in the form of chemical storage, which is what Sublime does more or less, right? Like it is
exactly
kind of has a battery embedded within it. You just wouldn't use that battery to do anything other than the one unit operation that it's supposed to do.
That's right.
Yeah. Okay, so understanding a little bit better then what electrochemistry is good at and why it's interesting in this context, I'm curious about what you feel like are the kind of frontiers of the space. Like, obviously, the biggest body of work in electrochemistry, at least as it applies to things that are commercial out in the world, is in battery universe, and there's like a whole host of different directions to take that. New battery chemistries. There's new materials for lithium-ion batteries, all sorts of different things. But then I think where you've also been a pioneer is in the application of electrochemistry into other sectors. We mentioned cement as a good example of that. What do you view as like the frontiers today? If you're looking out in the field and you're like seeing things that make you excited about the next 5 or 10 years in this space, what should we be looking out for?
Yeah, well, there's quite a few of them that are in my mind certainly at the moment. So first, if we go back and think about where are there examples of electrochemical processes that have scaled hugely, right? And a lot of people might say, well, isn't that hydrogen? Isn't that electrolysis? Turns out that that's not the one. It's really the chlor-alkali process, right? In which you take a sodium chloride solution, you make sodium hydroxide at one side, chlorine gas at the other side, and hydrogen at the same time. If you want to make HCl, you just react the hydrogen and chlorine. And so there are these standing examples of very large-scale electrochemical processes. And of course, you need to have the power supply to make all those things happen. If you look historically at where manufacturing operations that take a huge amount of electricity, not necessarily electrochemistry, but things like high temperature ceramics. Niagara Falls has been a favorite place because of the low cost electricity there, right? So if I think about what are the things that today look exciting, well, I mentioned mining earlier, right? And In general, I just think that reinventing these industrial processes that have gotten us to where we are and have primarily been based on thermal processes using primarily fossil fuels is a place where we just find new opportunities regularly. And about electrolytic iron production, what Boston Metal does, high temperature electrolysis, a molten fundamentally a molten iron oxide that you reduce to iron metal at one electrode, oxygen gas at the other. So that's on its way. My colleague Antoine Allenor, who worked on that, is now looking at molten sulfides, and that'll take another 300 degrees C or so off of that. And so I think there'll be a number of cases like that. But at the same time, we can think about bringing that all the way down to room temperature or close to. Okay. And so that would be, for example, it's a solid phase transformation, which I earlier said can be difficult, but it would be iron oxide to iron metal done electrolytically. Okay? And so this is an aqueous process. We have iron oxide in an alkaline electrolyte. If we bring that in contact with a metal electrode, we can reduce solid iron oxide to solid iron metal. Okay? And that then brings down the thermal load tremendously. And so reactions like that are worth thinking about how to make those more efficient in terms of both the what we refer to as Faradaic efficiency, electrons in versus product converted, and also voltage efficiency, how much of a overpotential you need to apply to make that happen. So those I think are interesting. There's others in the mining area that I am thinking about, but probably not mature enough to talk about just yet. But for example, we'd love to do mining of copper in a emissionless manner, right? And maybe there's an electrochemical route to doing something like that. Rare earth separations. One of the big problems we have with rare earths is that they're all chemically similar. But for a magnet, we mainly want neodymium and praseodymium. Okay? And it gives any chemist a chuckle when the investment community refers to it as NdPr, all caps. So, but neodymium praseodymium is now referred to as NdPr, right? But it should be capital N, capital P. Right? So separating those from all the other rare earths, which are chemically very similar. So in my lab here, one of my postdocs is looking at whether or not there might be electrochemical ways of doing that. So those are all there.
Would it be right to think from the highest level that like the hunting ground for electrification, but for electrochemistry is look for industrial processes that require a high temperature, and thus we generally burn fossil fuels to enact, and then explore whether you can do it electrochemically?
Yes, that are energy, not only a high energy, but concentrated energy intensity. Okay? And, you mentioned biology earlier. I tend to think of biology as processes which, in terms of their concentration, the energy is not, the total energy may be large, but the concentration of energy is not as high. Okay? In fact, there's an electrochemical example of that. I mentioned this 2D interfacial reaction issue. What matters to electrochemists most of the time is how much current you can get through a certain area of electrode, so-called current density.
Current density.
We talk about that all the time in a number of contexts. Well, a biological process, even if it has an electrochemical component to it, it's hard to get to high current density. Why is that? It's just that the molecules are large and bulky. Right? And inorganic molecules tend to be compact by comparison. Right? So high energy intensity, often inorganic, right? But those are the kinds of problems that I think benefit.
Right. I guess last question for you. We're obviously in an interesting moment with the vanguard of AI moving all the time and lots of different things. One area in which we've seen folks pushing for the application of these new AI capabilities is in and around electrochemistry, largely in the materials discovery world. Can you use AI to identify better catalysts? Can you use AI to identify better electrolytes that are well suited to particular materials you're going to use in a battery, whatever it might be? How much do you think, I guess from what you're seeing, do those capabilities exist today? Do they actually accelerate the discovery that you'd be doing in your lab or others are doing in their labs? And how much do you see that pushing the vanguard?
Yeah. So one thing I would point out is that this line of thinking is not as recent as you might think. So back in the mid-90s, we started to think about high throughput computation as a way of being more efficient about the experiments that you would eventually do. I still think that in the real world you have to do the experiment and show that you get the result that you might expect computationally. But so it's been since then that we first looked at whether or not you could compute a number of cathode structures, for example, and limit the number of experiments you'd have to do. That then developed into machine learning. And maybe you didn't have to do it quite so specifically compound by compound, but take where you could get it, a large database, and see if there were patterns. Right? So AI is just in a way, the natural evolution of that. If you were to look at the number of, for example, lithium-ion battery cathodes that have been truly discovered through this process, compared to those that were still developed by a good solid-state chemist's intuition, I think that intuition to this point still has won. There are a few key examples where I do think the computations led to the material. Disordered rock salt cathodes, I would say, is probably one of those. But on the other hand, it's getting better and better. And so I think it won't be, I think more and more examples of successful discovery through AI will start to result, right? Now, here's what my real question is. Yeah. Is this kind of discovery process, is it really invention, right? And so my question is, can AI invent? Right? And in a way, I feel like if you equate that kind of discovery with invention, we'll see that happen, but it'll be in a limited scope, such as it's a catalyst for a particular chemical reaction. It's a cathode for a particular type of battery. But can AI imagine a new system, right, that links together a number of different ideas, different concepts? I think a lot of the invention that's going on in clean tech today, and certainly the kinds of ideas that get me excited, are where you think about an entire system, where you have to do several things. You have to find a way to produce something. You have to find a way to use something. You have to find a way to dispose of or recycle something, all those together. And the invention is the whole system. So my question is, can AI do that kind of invention? And I don't know enough about it to give an answer. It'd be interesting what you think.
I don't think we know yet, but I think invention is the end of the spectrum. And look, if we never get to true invention, but actually do get all the way to, let's say you don't have to run the experiment ultimately because the computation is going to be sufficiently trustworthy that if you say, okay, hey, I've got this architecture and I'm going to use these materials, find me the perfect electrolyte, and it spits out the perfect electrolyte for you. If you get to that point, that seems like a pretty big leap in and of itself. It's not as far as saying, solve my problem of how I design a system to reduce iron electrochemically or something like that. But
yeah, that's a huge leap.
But if we just did the first thing, it'd be huge.
That's
right?
a huge leap. It frees us up to do the other kinds of inventing.
That's right. I mean, I guess what you're saying ultimately is that you don't think AI is going to put you out of a job, but it might make you a little more efficient in your work.
I don't think I have enough years left for it to put me out of a job, but I could be wrong.
Yeah. I don't know. I feel like you're going to be co-founding companies into your hundreds, but we'll see. Yeah, this was really fun. I greatly appreciate you singing the song of electrochemistry with me here.
Thank you.
Yetming Chang is a professor of material science and engineering at MIT. He's also the co-founder of at least 6 electrochemistry companies, including Form Energy and Sublime Systems. This show is a production of Latitude Media. Head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more at preludeventures.com. This episode was produced by Daniel Waldorf. Mixing and theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shail Khan, and this is Catalyst.